Welcome to the IEEE Future Networks podcast series, Podcasts with the Experts, an IEEE Future Directions digital studio production. Despite 5G's potential and favorable economics, deployment of the technology is proving challenging for a variety of reasons. In this episode, David Witkowski, co-chair, Deployment Working Group INGR, leads a discussion with Bill Hammett, president of Hammett and Edison, along with vice president of the company, Mathur. They share their insights on 5G deployment challenges and offer possible solutions in building out the next generation wireless infrastructure.
Hello and welcome to the podcast. I'm David Witkowski, the founder and CEO of Oku Solutions, and the chair of the Deployment Working Group for the IEEE Future Networks Initiative. Today, we're going to be talking about electromagnetic safety, RF safety, and how it applies to the deployment of cellular infrastructure in our society. I'm really pleased to be joined today by two people who have a depth of knowledge in this topic. William F. Hammett, who's the president of Hammett and Edison, and Rajat Mathur, who's the vice president at Hammett and Edison. Hammett and Edison is a consulting firm that works with municipalities and with the industry to bring science and fact to the topic of electromagnetic safety of cell towers and wireless installations. Rather than try to introduce them and their storied resumes, I'm going to let them do that themselves. Bill, why don't you go ahead and tell us a little bit about yourself?
Thank you, David. I'm a registered professional engineer in California and in other states as well. I manage a firm of 18. We're located in Sonoma, in the San Francisco Bay Area. And a regular part of our professional practice is the calculation and the measurement and the mitigation where it's appropriate of radio frequency exposure conditions. That's been my principal focus for 35 years. And in that time, we've done more than 20,000 site evaluations. And McGraw-Hill has published my book on this topic. As engineers, our job is really straightforward. What are the exposure levels and how do they compare to the standards? Since we deal just in facts, we work across the field, consulting for wireless carriers, for cities and counties, for broadcast stations, and for private landlords.
Thanks very much. Just for the purpose of the audience, can you mention the name of your book, please?
Yes, the book is Radio Frequency Radiation, Issues and Standards.
Okay. Raj, why don't you go ahead and tell us about yourself?
Hi, David. Great to be on this podcast. I'm really excited to talk about radio frequency exposure. I've been with Hammett and Edison for 19 years now. Like Bill, I'm a licensed professional electrical engineer in the state of California. I have a master's degree in electrical engineering. I'm an active member of IEEE ICES, International Committee on Electromagnetic Safety. ICES sets standards on radio frequency exposure, and I'm sure we'll talk more about that as we talk about RF exposure.
Excellent, thank you. So let's start off by defining the question here. Why are cellular sites generating health concerns? We know that even going back to the early days of cellular, there have been concerns about this. So the reason that we're talking about this topic today is because there's a public perception among some people that 4G and especially 5G technologies will have significant impacts on their lives, specifically around their health. And I think it's notable that this has been a challenge in the industry since the early days of cellular. So the question that I have, and I'm going to put it to Raj, is why are people concerned about these new technologies? What is generating that level of concern?
David, I think you're right about it going up and down in concern, and it generally tends to match the release of newer technology. So in my experience, when 3G or 4G was released, there was an uptick in concern regarding radio frequency exposure. And we're certainly seeing that now with 5G. And I think there might be several reasons why that's happening. Maybe there's not one clear answer, but maybe several things that could point to it. Specifically with 5G, it just so happened that at the same time as 5G was being developed and deployed, the FCC released or made available a bunch of frequencies, millimeter wave frequencies. These are frequencies that are generally higher in frequency than 6 gigahertz. And those frequencies have been in use. They're used in airport scanners. They're used by the police in speed detection. They're used in automobile collision detection. But this is probably the first time that these millimeter wave frequencies will be used for coverage purposes. Now, it's important to distinguish millimeter wave and 5G there. 5G doesn't have to be deployed on millimeter wave frequencies, and we can talk more about that, but that may be one reason why there's public concern around 5G, is that really the concern is for these new millimeter wave frequencies. Another reason might be that there's just a lot of information on the internet. Right before this podcast, I did a quick search on 5G health, and there were 573 million hits. And some of that is good information, some of that is not, but it's all there and it's readily accessible to anybody. And my last point on this would be that with 5G, and this actually started maybe a little bit before 5G was being deployed, is you're starting to see base stations go from being on taller towers and on rooftops of commercial buildings to smaller, lower power sites on utility poles and light poles in residential areas sometimes. And what that does is that, if you're living on your residential street, you may have had a base station a couple blocks away on a commercial building, and you may know nothing about it. But now, and maybe in front of your home or on your street, now there's a proposal for a small cell, a base station on a utility pole, let's say. And now you get more active, you get more interested in what is this thing, why is this thing, and that sort of dovetails back into going and doing Google searches and seeing what's there, and that brings up all kinds of information.
So I definitely agree with what you've said, which is, to recap, one, 5G is often associated with that millimeter wave technology, but in fact 5G could conceivably, in fact we're seeing that now, where it's being deployed in place of or in parallel with existing low band, below 1 gigahertz, mid band between 1 and 6 gigahertz sites that have been there in some cases for 20 years. And 5G can be applied to those frequencies. And of course, engineers know that modulation does not affect the potential health impacts, right? It doesn't matter if an FM transmitter has a safety zone around it where you shouldn't get closer to the antenna than a certain number of feet. It doesn't matter if that FM transmitter is playing Metallica or Mozart. The health effect is the same. The modulation has nothing. And 5G is that, it's modulation, at least when it comes to the air interface. So the other thing that I think you said that is very true is that because the network has been densified to provide more resources for subscribers, and of course our use of cellular technology is increasing exponentially and shows no sign of slowing down, the resources have to be placed closer to the users in order to provide that level of performance that people are coming to expect. So let's talk about the concerns that people have. So there are concerns about EMF health effects. And of course, there is a safety standard, which implies that there are some effects that are instituted in guidelines that come out from the IEEE C95, which I know, Raj, you work on that C95 standard. And so the question that I would pose to you, and I'll ask the question to Bill, what is real in these concerns, and what isn't real?
Well, the concerns are personal. People are concerned in some circumstances about their own safety. So there are a couple different ways to answer that question. In my personal and professional view, what is real is that anything below the standard, whether it's the IEEE standard or the INGR standard in Europe, if exposure levels are below that standard, I think there is no health effect. I understand the standards and the research that went into them and the conservative nature of the safety factors. So I don't think there's any real basis for a concern if it's below the standards. Some people feel that the standards are inadequate. They may feel that they themselves are personally susceptible to, particularly sensitive to electromagnetic energy. And it's not our place to tell them that they don't feel what they feel is true. Our role is to lay out the facts, explain how the standard is set and what it implies. And that's kind of a distinction for what is real, that is compliance with the standard, and what isn't is addressing how far below the standard people really should be concerned. There are a number of outfits that will use measurement equipment that isn't calibrated or won't even go up as high as the standard itself. They're measuring very low levels, but they are triggered to be alarmist. That is, at low levels, hundreds or thousands of times below the standard, they'll still register bright red lights or top out, and this just exaggerates people's concerns. And I think in terms of the standard, what they're measuring, what they're purporting to measure, just isn't real because it's all well below the standards.
Okay, thank you. Yes, I think having looked at the equipment that is used for measuring this, and having worked in the test and measurement industry myself, there's a huge difference between a $6,000 piece of test equipment that has a NIST traceable calibration and a $125 EMF meter that you buy off of Amazon or in Home Depot. I'm going to put a question to Raj, which is, could you describe for us what the margin is between where an effect can be measured on the human body and where the safety guidelines are set?
Yeah, absolutely. The FCC public limit, and really the public limit for all these standards that Bill was talking about, IEEE and INGR, is set with a safety factor of 50. So the first effects are observed at levels that are 50 times higher than the standard. And I'm going to just ask the question because I think it's a reasonable question, is what are those effects that are observed at levels 50 times higher than the standard? And that effect is heating. There's a 1 degree rise in temperature at those levels. There's an example of how that's actually put to use for us is a microwave oven where you have extremely high radio frequency levels inside a microwave oven. And those generate heat by vibrating the molecules, generally the water molecules in the food. And that's the mechanism that heats up your food. So that's an example of what happens in extremely high radio frequency exposure. Now, relating that to base stations, we're talking about levels at ground and people's homes that are, we typically measure to be less than 1% of the FCC limit. So that's 100 times below the FCC limit. And remember, I said that the first effects were at levels 50 times above the limit. So there's this 50 times safety factor plus levels are 100 times below the limit. So you have this massive margin in place for what people normally experience in their day-to-day lives versus where the first effects were observed.
The margins that you describe are certainly large. I think an analogy probably helps here, and I've used this analogy myself in some of the conversations that we've had with local governments. Imagine a speed limit on a freeway is 65 miles an hour. 50 times, so that we would say that that's the safe speed at which you can drive on that freeway and know that you're going to be okay. The 50 times below that is 1.3 miles per hour. Right. So we would, it'd be, imagine getting on the freeway and driving 1.3 miles per hour because you have that margin that you've inserted in that. Is that a fair way to look at that? Do you think that's a reasonable analogy?
Yeah, I think I would maybe change it slightly to say that if you think, or if your studies show that the safe speed is 65 miles an hour, then you are setting a speed limit of 1.3, because that's sort of what we're doing. There's all these studies that show, hey, what's the safe level? And then you apply a 50 times safety factor to it. So 65 miles per hour is what your studies show is the safe speed limit. And then you set the speed limit at 1.3 miles an hour.
I don't think Sammy Hagar would be okay with that. For those of you who remember that song, I Can't Drive 55. So, okay, so let's talk about the history of research that's been done on the effects of electromagnetic fields on living things. Bill, can you give us a history? How long has this been going on? How many studies have been done, et cetera?
Sure. It's a good question, and it's remarkable how far back people have been assessing and been aware of the potential for danger at high levels. Radar in the early days of that, following World War II, were a common source of high magnitude fields. And the Navy, I know, did a lot of research on that topic because they had personnel working around radar facilities and wanted to know. And so they started developing standards. ANSI, the American National Standards Institute, actually had a 1974 standard that was one of the precursors of what we have today. So it's been an actively studied field. So the research that's been done is extensive, and research for quality needs to really have two impacts. One is it needs to be peer reviewed, where a researcher will publish all of his data that's collected from the experiments, and that allows other independent people to look at the data and see if they can draw the same conclusions from the same data. So that's a peer review process. Replication is the other aspect, where one researcher in one institution may find what he thinks is a causal relationship, but there are lots of extraneous factors he can't can't account for. So until another researcher in some other institution with a different set of extraneous factors they can't control for finds that same causal relationship, then it starts to have some scientific merit. So single studies are interesting, but it's only in collection with other studies seeking the same type of investigation that you get scientific merit coming out of it that the standard setting bodies can use for establishing their standards.
That's really interesting. And I think that's probably one of the biggest challenges that we face in talking to the public and to local governments about electromagnetic safety, which is understanding the difference between correlated data and causal relationships. There's a great book called Spurious Correlations that came out a few years ago that has a lot of funny correlations in it. The divorce rate in Maine correlates at 99.26% with the per capita consumption of margarine in the United States. Divorce rates in Maine and margarine are not causally related. The data is correlated, but there's no relationship between those. And so I think with the general public and especially with non-engineers and non-scientists, it becomes really important for us to be able to explain the difference between correlation and causation, which can be a bit challenging. Research on this topic, of course, is ongoing. One of the, the standard for this is, in fact, the IEEE C95.1 standard, which was just updated in 2019. Raj, you're directly involved in that standard work. Could you give us an overview of the 2019 update and talk about C95 in general and how long has it been going on? And what are the findings from C95.1?
Yeah, I can. So I've been a member of ICES for about 12 years now. So the previous, you mentioned that there was a new release, or standard is called C95.1, and the new release was last year in 2019. The one before that was in 2005, 2006. So I wasn't involved in that, but I was extensively involved in the C95.1 in 2019. And there's also a bunch of associated standards that go along with that, and I'm involved with those too. The general process is that there's a literature review team that's a sort of a subset of the members of ICES, and these are folks who are involved in the research, actively involved in research, professors and researchers in the field. And so, as Bill mentioned, they're looking through these studies, looking at peer-reviewed studies, replication, and then when we meet, which is typically twice a year, and sometimes email exchanges in between, they'll give us an overview of what the latest has been in approximately the last 6 months. And we use that research. And I should say that all these studies are, or at least the names and the abstracts, are available for people to look at. There's the IEEE ICES website, which lists the names and abstracts of all these studies in its standard, but also, like I said, on the website. And then the World Health Organization has a real nice database of these studies as well. So if you look at that, there's in the IEEE website, there's almost 4,000 studies. And that's the basis for the standard. And it's really quite extensive. The standard, I should add, is available for free to download. And so I encourage your listeners to download the standard. it is a long, extensive, and technical document, but there are, certainly a bunch of sections, particularly where the rationale is described, where they go into real detail on all the elements that were looked at, what the research shows, what the findings are, and what the conclusion is. And there's a whole bunch of studies on various aspects of radio frequency exposure cited at the end of the standard. I should add that there's other standards as well. There's, which we touched on, the FCC standard, and there's the European standard, which is called INGR, and that also has been adopted by a number of countries outside Europe. Those, I would say, are the three big standards.
And Raj, correct me if I'm wrong, but the FCC doesn't have a lot of engineers working for them. In fact, it's mostly lawyers. I mean, the IEEE is really the basis of the FCC's standard. They derive their standard from C95. Is that correct?
Yes, partially. So the FCC standard was originally set in 1996, and it was actually a congressional act, the 1996 Telecommunications Act, that asked the FCC to set limits, which they did. And what they did was they took two standards at the time. One was the IEEE standard. I believe it was the 1992 standard that would have been active at the time. And then another standard, NCRP, National Council of Radiation Protection. Those were the two major standards, scientific standards in existence at the time. And what the FCC did was they sort of used both those standards to create the FCC standard. Now, since 1996, the FCC, and most recently as just like late last year, has said that they've looked at the existing research and existing standards, and they find no basis to change their limits. Since that time, the IEEE standard, the basic restriction of the IEEE standard, the 50 times safety factor that we spoke about, is unchanged. And so that's, I believe, what the FCC is looking at, that the basic restriction hasn't changed. And so they have no basis to really change their standard.
So one of the things that I think causes people to react negatively to electromagnetic radiation is the use of the word radiation, especially for older people who grew up during the Cold War. They remember the duck and cover drills, the threat of the Soviet nuclear weapons, and all that. That nuclear age, if you will, I think firmly cemented radiation and the word radiation as a negative thing in people's mind. But when we talk about electromagnetic radiation, there's a difference there. Bill, could you describe for our audience the differences between electromagnetic radiation and these types of nuclear radiation that they may be more familiar with?
Sure. There's a huge spectrum of electromagnetic energy, electromagnetic radiation. And radiation as a term just means dispersal. If you drop a pebble into a pond, the energy from that action of breaking the surface will create ripples, and those ripples radiate out from where the stone was dropped. There's nothing particularly no connotation to the word radiation that should be alarming. It's just a dispersal of energy. But I do want to talk about the electromagnetic spectrum, which is a broad spectrum that goes from direct current is at zero, and as soon as you get stuff that comes out of the wall socket, and electric power coming out of the wall socket is plus minus 60 times a second. That's 60 cycles. We call it 60 hertz. That's the ELF, extremely low frequency, for electric power. Power lines running overhead operate at 60 hertz. So wavelength at 60 hertz is here to New York. I say here, I'm in San Francisco, but 3,000 miles is one wavelength at power frequencies. So we don't deal in that frequency range. We deal up when you get higher frequencies in radio frequencies. And it's a big chunk of this electromagnetic spectrum that is good for communications. The atmosphere blocks solar radiation in that frequency range, so it's very useful. AM radio was one of the first applications of radio frequency commercially that people might recognize. A wavelength at AM frequencies is about 1,000 feet. It includes FM and TV, where wavelengths are on the order of 10 feet. It goes higher as well, and it's a packed spectrum of assigned frequencies assigned by the Federal Communications Commission for ship-to-shore and aeronautical and Secret Service and police and fire. It's packed with assigned frequency bands, everybody doing their own operation in their assigned frequency bands. Above radio frequencies is a big chunk of spectrum called infrared. And we use that to control our TVs. You have an infrared controller. If you put it behind the sofa, it doesn't work real well. The wavelengths are now getting short, less than an inch, shorter than that. And the energy tends to travel in a very straight line. And above infrared is a tiny, tiny sliver of this electromagnetic spectrum. We call it light because our eyes happen to be sensitive to it. Above light is ultraviolet. And when we speak before groups, we always ask, well, what does ultraviolet do? And people mumble, and then somebody will say sunburn. That's exactly right. The ultraviolet, the wavelength of this above light is so short that it'll get into molecules and break off an electron. That process is called ionization. A very well understood principle, effect of the high frequency radiation. During the pandemic now, a lot of people are installing ultraviolet purifiers for air. You see it. I saw a TV special not too long ago about some restaurants putting this in and pulling air over the ultraviolet light in order to disinfect it, because the wavelength is so short it'll get in and break off electrons in the virus or in bacteria. Pools will often use ultraviolet light for disinfecting the pool water. Above ultraviolet is X-rays. And I asked the question, what do they do when you go to the dentist and take an X-ray? Well, they put a lead shield over you because they know that that's causing a little bit of damage, and they want to minimize the amount of damage. And of course, where do they stand when they push the button? They stand around behind a wall to get even more protection. So those are examples of ionizing energy, where the nature of it is to get into molecules and break off electrons, and that causes a little bit of damage, and that damage adds up over time. What the carriers are using is not X-rays, it's not ultraviolet, it's not light, it's not infrared, it's down in this big chunk called radio frequencies, where wavelengths are on the order from 1,000 feet down to an inch. And that's a well understood principle. This is non-ionizing energy. There's nothing dangerous about it per se. It's just a question of magnitude, as Rajat described earlier. High magnitudes cause an impact. That's why the FCC and all the standard setting bodies have a 50 times safety factor included for unlimited exposures 24/7.
Thanks, Bill. That's an excellent overview of how photons and electromagnetic energy work across the spectrum, ranging from power all the way up beyond visible light to X-rays. One of the things about millimeter wave that you touched on was that it is very line of sight. And when electromagnetic radiation is line of sight, tends to not penetrate material very well. Raj, would you please talk about how millimeter wave cellular signals behave and how they're different from the cellular signals that we're used to?
Yes, I can. So as Bill did an excellent job of describing the whole electromagnetic spectrum, if we sort of hone in on the radio frequency part, which as Bill noted is non-ionizing, we have the lower end, we've got AM frequencies, which travel really long distances. And in some cases, when the atmospheric conditions are right, they'll bounce off the ionosphere and can travel even further. And that's because, they have long wavelengths. When you get to the other end of the radio frequency spectrum, where the wavelengths are shorter, the signal just doesn't travel as far. In addition, as you noted, David, it can be severely attenuated or its magnitude reduced by things like clothing, by foliage, and in some cases even by raindrops, by rain. And the upshot of that for the wireless operators is that these signals just don't go very far, and so they need several sites closer together. And that sort of touches on what I was talking about right in the beginning of the podcast with requiring sites, base stations in residential areas and utility poles closer together. The other aspect of millimeter wave, or I should say a related aspect, is as related to RF exposure, millimeter waves don't penetrate beyond the upper layer of the skin. They don't get into where our vital organs are. It's just, in fact, there's a word for it. It's called the skin effect at these frequencies. And it's a surface effect. And so when I talked about the heating, if you had, let's say, a microwave oven that you used millimeter waves, just the surface of your food would get heated up, not the inside of your food. And so microwave ovens actually use lower frequencies, 2.3 gigahertz, because those are able to penetrate into the food and heat it up. Millimeter waves can't do that, just by the very nature of the higher frequency and shorter wavelength.
And let me add also to what Raj was saying about the deployment of sites at low elevations for the millimeter waves, because they're don't travel as far. They don't put as much power into those bands. We typically see things less than 200 watts peak power out toward the horizon from a pole mounted, whether it's a light pole or utility pole, in the millimeter wave bands. So they're building networks for very high capacity because of the higher frequency and the wide bandwidth that the government has assigned to them. They get a huge data capacity, and so the potential for all kinds of new uses is very enticing. But the facilities themselves are not the high power facilities that you see on rooftops or poles or along the freeways, those kind of facilities. These are low power, short distance facilities that, because of their low power, are not presenting very large exposure levels in neighborhoods. That plus the inverse square law that we haven't talked about, but is really a key factor as well in terms of the energy dissipating by the square of the distance. The power drops exponentially. Those factors of low power to start with, plus the inverse square law, makes the exposure levels near these new facilities going in neighborhoods as low as they are.
Thanks both. very much agree with what you're saying. And in fact, recently I had an opportunity to demonstrate it to myself. I was in one of the cities in the San Francisco Bay Area where they have the millimeter wave 5G deployed. And it was the first time I've had a chance to do a speed test on it. And my interaction with this site was very interesting. First of all, when I stood directly next to the pole, I did a speed test and noted that the speed was, at a certain level. And then as I moved 10 feet away from the pole, I did another speed test and found that in fact it was faster. And of course, we know that information throughput and energy are correlated through Shannon-Hartley, which relates the ability to put information through a channel based upon a variety of factors, but primarily driven by the signal-to-noise ratio. So then as I moved away from the site, I noted the speed tests were slowing down, and then I walked around a corner, and the moment I walked around the corner, the signal was gone. It just completely disappeared. I think you're right in that we do want to talk about the inverse square law. So Bill, why don't you give us an overview of what that means in the inverse square law?
Well, the inverse square law just simply says that at some distance from a power source, if you double the distance, the power is going to go down by a factor of 4. 2 squared, 1 over 2 squared. It's going to go down to a quarter of the power. If you go 10 times as far away, it's going to go down by a factor of 100, 1 over 10 squared. So the power level is dropping rapidly. The phones, the devices, don't need much energy to operate. They have tuned receivers and are good at picking up the signals. In terms of exposure conditions, the levels are dropping very rapidly. And so that is one of the factors that ensures that these facilities do comply with the federal standard. The other factor, of course, is the directivity of the antenna. You mentioned when you were directly under the pole, you got a certain amount of speed on the speed test. And as you moved a little bit further away from the pole, you got higher levels. And that's indeed the case, that there's hundreds or thousands of times less power going down than there is going out from these antennas. They're highly efficient. They want to send the energy halfway out to the next cell site, to the next site in the carrier's network. So those factors all work together, low power to start with, inverse square law, and the directivity of the antenna. Okay,
Bill, Raj, that was an excellent overview. Thank you for explaining inverse square law. This has been a great podcast. I think we've covered a lot of ground today, a lot of good material here. I really want to thank you for your time and for the work that you do. Bill, why don't you tell our audience how to get a hold of you if they'd like to?
Yes, I'd be happy to. And I too enjoyed the conversation today. It's a fascinating field. I think we had a lot of good information. We view our role as reporting and explaining the facts, and the facts tend to speak for themselves. And so if people are interested for further information about this or further discussion, we can be reached at our website, which is www.h-e.com. Always happy to have inquiries. Again, thanks for the opportunity to participate.
Thank you. And thank you, Raj, for being here today. Are there any resources that you'd like to let the audience know about?
Yeah, and I'd like to just reiterate that there's a lot of good information available at the IEEE ICES website, including studies for those interested. There's great information at the World Health Organization site. The FCC has an RF safety page. ICNIRP, if you're interested in international standards, has some excellent information as well.
Thank you both for being here today. And thanks for joining the podcast. Have a great day.
Thank you for listening to this edition of the IEEE Future Networks podcast with the experts. Discover more about the IEEE Future Networks initiative and inquire about participating in this effort by visiting our web portal at futurenetworks.ieee.org.